In this lesson, we're going to learn how to write the equation given the graph of a polynomial function. So what we need to do first, I've kind of filled in the note sheet because this is actually review. We did this note sheet in Unit 1, so you could rewatch that video. But a polynomial function of degree n is a function of the form p of x equals, and then you have all these terms here. We talked about how you want to have your function written in descending order so you can see the leading coefficient. So descending order means you take the highest exponent, write its term first, and then each exponent that's lower goes after. So this is the leading term. When a polynomial is all multiplied out with all these terms added or subtracted together, it's called standard form. And standard form is only good for two reasons. One, for the leading term, and also for the constant. So if you look at this one, 3x to the 5th plus 6x to the 4th minus 2x cubed plus x squared plus 7x minus 6, this is your leading term, and it's going to have the greatest influence on the end behavior. And this is your constant term. And if you put 0 in for all these x's here, they all will go away. So this constant term gives you your y-intercept that shows up on the graph. So those are the two terms in the multiplied out form that matter. And so we really don't bother multiplying out. So let's move on. To review, the degree of the polynomial and the coefficient of the leading term tells you the shape of the graph and its end behavior. So the odd degree, if you have a polynomial that has a leading term that has an odd degree but a value that's positive, that's going to cause an increasing function, and it's going to have down-up behavior. Okay, so it will start down and then end up. And this is review. That means that as x goes to the right, as the x coordinates go to the right, the y coordinates are going to head towards positive infinity. And as x goes to the left, or as x goes to negative infinity, the y coordinates are going to go to negative infinity. So that's where the down up comes from. But you go left to right, so down and then up. If you have an odd degree here, like this 3, but a is negative, it's going to flip that upside down, and it's going to be up-down behavior. So as x goes to the right, the y coordinates f of x are going to go down to negative infinity, and as x goes to the left to negative infinity, the y coordinates are going to go up to positive infinity. So that's up-down. So notice that the odd degrees, the behaviors are opposite. Okay, if we look at even degree, if you have an even degree leading coefficient, a leading term with like a 4, but this a is positive, that's going to go to up end behavior. That's just like y equals x squared, and we know what y equals x squared looks like. It's got an even degree of positive a value. So as x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to infinity. If we have an even degree like this 6 exponent, but a is negative, it's going to flip that from up to down. So as x goes to infinity, y goes to infinity, negative infinity, and as x goes to negative infinity, y goes to negative infinity as well. So that's just a review, and that can help you check your work as we write the equation of the polynomial. Alright, so number 3, a polynomial in factored form, not multiplied out, is very useful because we can easily find the x-intercepts or the zeros of the function. So this is a function that is in factored form. These are being multiplied together, and we would not want to multiply this out because when it's in factored form you can easily tell the zeros. So I'll do this the long way. The zeros are the x-intercepts. To find the x-intercepts, remember you always set y equal to 0. So if I set this equal to 0, these factors times each other equal to 0 by the zero product property, x minus 3 equals 0, or x plus 4 equals 0, or x minus 1/2 equals 0. One of these has to be 0 because something is being multiplied to turn the numbers to 0. Anything times 0 is 0. So if you solve this, you get x is 3. If you solve this, you get x is negative 4. And if you solve this, you get x is 1/2. So I'm adding 1/2 to both sides. That's what I subtracted 4 here, added 3 here. So the zeros of this function are 3, negative 4, and 1/2. So hopefully you'll learn how to just look at these factors and figure out what the zeros are. It's always the opposite of what you see because you're always going to be adding the opposite to get x by itself. Okay. The next thing, when it's in factored form, we have to know about something called multiplicity. In general, if c is a 0 of p, the polynomial, and the corresponding factor x minus c occurs exactly m times in the factorization of p, then we say that the 0 c has multiplicity m. That's very complicated, easy to understand if you're looking at an example. Okay, so here is an example, and first thing we want to be able to do is find the zeros. Okay, so again, if we do it the long way, if we say let y equal 0, then x equals 0, or x plus 3 quantity squared equals 0, or x minus 6 to the third equals 0. So we have x is 0. Notice that people leave that 0 off a lot of times when it's just x. Here, if I take the square root of 0 is 0, leaving me with x plus 3 equals 0, so x equals negative 3. So see how that square does not affect the 0. Here, if I take the cube root of both sides, that gives me x minus 6 equals 0, so x equals 6. So the zeros are not going to change when there's an exponent. So the zeros are 0, negative 3, and 6. And I can't say this enough times. If you just have an x, the 0 is 0. People just don't like that because it doesn't look like these, but we could make it look like it if we just made that x minus 0. So don't forget that that's a 0. That's a factor and it has a 0. Alright, now the multiplicity is just the exponents that go with them. So this x is x to the 1. So this 0 has a multiplicity of 1. This x plus 3 has a square, so this negative 3, 0 has a multiplicity of 2. And this x minus 6 has a exponent of 3, so this 6 has a multiplicity of 3. So that's multiplicity. It's just whatever is here. And it just means that you count it this many times. So you count this 0 3 times, you count that 0 2 times, you count that 1 time, and I'll explain what that means as well. Alright, let's keep going. Alright, so here's what you need to know about multiplicity in terms of the graph. The multiplicity of each 0 determines how the polynomial p of x will behave when it gets to the x-axis. Okay, so we've talked about end behavior. We know about odd degree, down, up, or up, down, even degree, up, up, or down, down. But now we're also going to be looking at the multiplicity and look at the behavior at the x-axis. Okay, so if the multiplicity of the 0 is 1, then it's just going to go straight through that 0. Okay, if the multiplicity is odd, like m is 3, or m is 5, or m is 7, then what's going to happen, it's going to bend through that 0. So if you have the 0c, and it was like x minus c to the third power, what would happen is if you're starting out down here, when you get to this c0 here, you're going to kind of flip it, like if this were kind of a parabola shape, an upside down u, when you get to this 0, you're going to flip it back to an upright u. And if you start up here, you'll come down like looking like a U, and then when you get to the 0, you're going to flip it to an upside down U. So an odd multiplicity is going to cause a bend. Now what happens as the multiplicity gets larger is it just sort of flattens out. The larger the multiplicity, the more flat it looks, but we don't really worry about that in this class, but that is what's going to happen. If you were to graph y equals x to the third, y equals x to the fifth, you'd see that flattening out process at the 0. Alright, if m is even, like if the multiplicity was 2 or 4 or 6, it's going to cause a bounce at the x-axis. So if you have your 0 c and you have x minus c squared, if you're coming from above, it's going to go to that 0, and then when it hits it, it's going to bounce back up. If you're coming from below it, when it goes up to that 0 and hits it, it's going to bounce it back down. And again, the higher the even degree, the flatter it will look. The behavior is not going to change, it's going to get flatter. Alright, so we're going to use this information to write a polynomial equation. Okay, so here is our first example, and what we have to do is we have to figure out the zeros first. Then we have to figure out the multiplicities of those zeros. Table, so you can kind of keep it organized. This graph is a little bit oddly numbered. You always have to make sure you pay attention to how it's being numbered. So I'm going to say this is 1, 3, 5, -1, -3, -5, -7, and then up on the y-axis we're counting by 2s, 2, 4, 6, and -2, -4, -6, -8. Okay, so we have to find our zeros first. So I'm going to go left to right, and anytime the 0 means x-intercept, so we have a 0 at -5, and we have it's going through the x-axis at -1. And it's going through the x-axis at 3. This 0, 2 is not a 0. That's a y-intercept, not an x-intercept. Okay. The multiplicity, that's why we just learned this. If it's a bounce, it's got an even multiplicity, and we're always going to just use 2. If it has a bend, it's got an odd multiplicity, and we're just going to use 3. If it's going straight through, the multiplicity is 1. Okay, so this 0 is coming up and hitting it and bouncing, so this has a multiplicity of 2. This 0 of -1 is going straight through it, so that has a multiplicity of 1. And this, another bounce, multiplicity of 2. Okay, so every 0 can be written as a factor. A 0 is a number, it's an x-intercept. A factor is when you have x minus in front of it. Okay, and so every 0 can be turned into a factor. So the factor that goes with -5 is x minus -5. But what is that? That's x plus 5. And then the multiplicity is the exponent that goes with it. So we have x plus 5 quantity squared. The 0, -1 would have a factor x minus a -1 or x plus 1, and its multiplicity is just 1. So we don't really even need to write that, but I did. Okay, the next one, the 0 here would be the factor x minus 3, and then the multiplicity is 2 squared. So then after you find your zeros and their multiplicities and their factors, step 4 is you have to write the polynomial. But this is interesting. There is another number that you're going to need to find. Okay, so our polynomial is p of x equals a times x plus 5 quantity squared times x plus 1 times x minus 3 squared. Now what is that a? That a is very important, and people always, not always, sometimes forget to find it. You know, really important, and I wanted to show you through Desmos why that is important. Okay, so in Desmos I have put in a bunch of functions, and I've only got one graphed. This is what the factored form that we just found, this polynomial, looks like if a is 1. Okay, this is what it looks like if a is 2. So it has the same zeros, but it's a completely different looking graph because it got vertically stretched by a factor of 2. This is what it would look like if it had a value of -2, another different graph. This is what it would look like if it had an a value of 3, vertical stretch by 3. So in fact, the a value, if I click play here, look at all the different polynomials that have these same factors and these same multiplicities but a different a value. Just look at that for a minute so you can remember how important it is to find a. A causes a vertical stretch or a vertical shrink or a flip. So a matters and you have to find a. So how do we find a? Well, because this polynomial could be a bunch of different shapes, what you have to do is you have to find a point. A lot of times we'll give you that point. You might have to read it off the graph yourself, but we have highlighted the point 0, 2, and it's just a coincidence that's a y-intercept. It could be any point. And so just like with exponentials, we're going to say, well, let's let x be 0 and y be 2. And plug it in so that we can find the value of a. So don't get it backwards. This is y. So 2 would go in here and 0 would go in for x in all the places that you see x. Alright, so many times people make a mistake with the arithmetic here. So you really want to use your calculator if you need to, but for this one, I'll just go ahead and do 0 plus 5 is 5. 5 squared is 25. That's going to give you 1. And then -3, quantity squared, isn't -9. It's +9. Okay, so then 2 equals, we need to figure out what 25 times 9 is, times 1, which is 225. So 2 equals 225 times a. Here's another error people make. They divide by the wrong side. You're trying to get a by itself, so you want to divide both sides by 225. Okay, so a equals 2 over 225. So we found a, so then the last step is make sure you finish it all the way out, demonstrate that you understand a is 2 over 225, and my factors are x plus 5 quantity squared times x plus 1 times x minus 3 squared. There are an infinite amount of polynomials that have these same zeros with these multiplicities, but only one that has these zeros and that a value. And you can check your work. This has down-up behavior. Okay, so we would expect a positive a value and an odd degree. So really quickly, we don't want to have to multiply this out. Please don't multiply it out. And people are going to multiply it out even though I say you don't have to. Happens in my seated class all the time. All you have to do when it's in factored form, if you want to find the leading term, is just multiply this leading coefficient times x squared times x to the 1 times x to the 2. And x squared times x to the 1 times x to the 2, you just add the exponents. So the leading term would be 2 over 225 x to the 5th. Okay, and that you can use to check your work. Is that an odd degree looking graph? Then that means that you did it right. Is a positive, down, up? So you've got that one. Okay, so let's look at this next example. It is from the lab manual, number 4. And again, the first thing we want to do is we want to locate the zeros, their multiplicity, turn them into factors, and then find a. So we have a 0 of -2, and it's a bounce, so that's 2. So that would give me x minus a negative 2 or x plus 2 quantity squared. So remember, the 0 and the factor, they're going to be opposites. Because of the way you find a 0, you subtract 2 from both sides. Okay. The next 0, not this y-intercept, nope, this x-intercept, which is right here at 1. So, and it, look at that motion there. That's going upside down u, gets to the 0, turns to a right side up u. So that's got a multiplicity that's odd, so we'll use the number 3. Okay. So then that factor is x minus 1 cubed. And then we have a third 0 right here at x equals 3, and that multiplicity is 1 because it's going straight through. Alright, so we can now write the polynomial, but we need to remember to put the a there. So p of x equals a times x plus 2 quantity squared times x minus 1 cubed times x minus 3. Okay, do you remember how to find a? Well, there are an infinite amount of order pair of functions that can have these same zeros, but only one that goes through the point 216. So this is my temporary x, and that's my temporary y. So I'm going to put 16 in here, and then 2 everywhere I see an x. And this time I will use the calculator to show you. So we're going to get 16 equals, all right, you can put it in just the way you've written it down. So parentheses 2 plus 2 squared, parentheses 2 minus 1 cubed, parentheses 2 minus 3. It'll keep you from making an arithmetic error. I see so many arithmetic errors. All right, you get negative, this is a times negative 16, so I'll write it as negative 16a. Then I want to solve for a, so I'm going to divide by negative 16. So a is equal to negative 1. So the last step, just take this polynomial that you wrote here and just rewrite it, but now we know that a is negative 1. And then if you want to use other knowledge, this in behavior is down, down. Your a is negative. That makes sense. Add up your degrees. 2 plus 3 is 5 plus 1 is 6. So negative 1x to the 6 is the leading term, and that does cause a down, down graph. Okay, so the last one, number 7, the zeros, the multiplicity, the factors. So we have a 0 at 1, and it's a bounce, so that's 2. So x minus 1 squared is a factor. And then you have another 0 at 3, and it's going straight through, so that gives you a factor of x minus 3 to the 1. So let's find a. Don't forget, a times x minus 1 squared times x minus 3. And we're going to use the point 2, 1, because that's what was given. Alright, so that's x and that's y. So 1 equals a times 2 minus 1 squared times 2 minus 3. 1 equals a times 2 minus 1 squared is 1 squared, that's 1. 2 minus 3 is negative 1. That's where people mess up, is they don't remember their negative rules or just lose a negative. We get 1 equals negative 1a. Divide both sides by negative 1. A is negative 1. So our polynomial for number 7 is negative 1 times x minus 1 squared times x minus 3. And I will say one more time, you do not need to multiply that out. You can leave it in factored form, because all you need from multiplied out form is the leading term. We know that's negative 1x cubed. Okay, so the last one on this note sheet says find a polynomial with real coefficients that satisfies the given conditions. Q, that means name the function q, and it has degree 3. So when we finish up and check our work, we want to make sure it ends up to be a degree 3. It has 3 zeros, 2, negative 5, and 6, so that means all their multiplicities are going to be 1, and it has a leading coefficient of negative 2. So that's just going to be q of x equals negative 2 is where your leading coefficient goes. If the 0 is 2, the factor is x minus 2. If the 0 is negative 5, the factor is x plus 5. If the 0 is 6, the factor is x minus 6. Degree 3, 1, x to the 1, x to the 1, x to the 1, that's degree 3, so we don't have any multiplicities, and that's it for that one. Okay, so that leads us to this last one, which is really kind of tricky. Alright, so it's important, but I'm going to throw some new things at you. It says the degree is 6. First tricky thing is that the zeros are fractions. Okay, so that is not that bad. We'll do it this way. We'll write the zeros. Okay, so the first thing it says that you got a 0 of 3/4 and a 0 of 1/2 and a 0 of negative 4 and a 0 of 3, but the zeros at negative 4 and 3 have multiplicity of 2. Okay, so if you remember to make factors, it's just always x minus, x minus, x minus, x minus. So if the 0 is 3/4, the factor is going to be x minus 3/4. If the 0 is 1/2, the factor is going to be x minus 1/2. If the 0 is negative 4, but the multiplicity is 2, it's going to be x minus a negative 4, which is x plus 4, and then the multiplicity is 2. It's the opposite of what you see. Okay, if the 0 is 3, then the factor is going to be x minus 3, and the multiplicity is going to be 2. Okay, but not so fast. Alright, we don't like our factors to be fractional. We want to turn them into integer factors. Okay, so what's going to happen is a 0 is when you set it equal to 0. So I'm going to set this equal to 0 because that's how you find this 0 here. So that's legal. And I'm going to get rid of this fraction by multiplying both sides by 4. Okay, so if I multiply this by 4, I get 4 times x is 4x. And then 4 times 3/4, they cancel. The 4's cancel. So we end up with 4x minus 3 as my new integer factor. Alright, I showed you how to do it, but maybe you'll see a shortcut. So if I set this equal to 0 and I multiply both sides by 2 to get rid of the fraction, that's going to end up with 2x minus 1 because these two cancels. Alright, so what's the shortcut? So if you see a rational 0, all you have to do to turn it into an integer factor is take that 4 that's in the denominator and put it in there with the x. So x minus 3/4 is 4x minus 3. To change x minus 1/2, you take that 2 that's in the denominator and put it in there with the x, 2x minus 1. So it's really easy to turn these fractional zeros so that they have integer factors. Okay, but then there's another trick. Okay, so let's write this. So it says the leading coefficient is 16. Okay, so I'll do it wrong. This is wrong. So that means you would put, maybe you'd think, I'm going to put 16 in for A. That's easy. Leading coefficient 16, and my factors are 4x minus 3, 2x minus 1, x plus 4, quantity squared, x minus 3, quantity squared. So the question is that leading coefficient really 16? Well, if you have, remember the leading coefficient comes from the multiplied out a factored form. Now I don't want to multiply the whole thing out, but I can find the leading term if I multiply these x's in their squares. So 4x times 2x is 8x squared times x squared, which would be x to the 4th. I'll write that down. 4x times 2x times x squared times x squared. This is how you find your leading term. That's 8x to the 1, 2, 3, 4, 5, 6, 8x to the 6. but there's already a 16 out here, so 16 times a is not going to give you a leading term, leading coefficient of 16. So you've got your 8x to the 6th in here. So that's, you got to take away from that 16. You got to understand that we've got 8x to the 6 here. So what times 8 will give you 16? And it's really just 2. So that's a little bit tricky for 2 reasons. Okay, so we've learned how to get rid of the fractional factors. We don't like that. We want integer factors, but because you put these numbers in front of the x, that's going to affect what your a value is, because you have some values in here that you have to account for.